So hello, and today's topic is that hybridization for the diffusion system. So in general, mixed systems, we have many of those, like definite or indefinite, like Darcy problem in hydrodynamics, heat diffusion, Maxwell's equations, and so on, of course. But one of the largest classes of those are probably the convection-diffusion systems, which appear in many applications. And we may write them, for example, in this form. So we have some vector flux Q and scalar potential U, then some conductivity kappa, and some velocity field one of C. For this talk, consider that flux is being discretized some continuous elements like rubber, atoms, netherlight, and so forth, or also discontinuous fluxes. I will get to it just in a minute. And for potentials, we always consider DT elements, so we can benefit from things like local energy conservation, stimulus, things. And when we formulate this in free form, we obtain like block symmetric or antisymmetric structure. But I should point out that it's not truly symmetric, like element-wise. That's very important because, for example, A can be asymmetric due to anisotropic diffusion, or B is symmetric, one of convective terms. My second cornerstone presentation is hybridization. So we introduce some Lagrange multipliers, lambda, which live only on the skeleton of our mesh. And we can then break the continuity of our elements and reduce the system only to these phase values, skipping basically that interior degrees of freedom which do not exchange any information with neighboring elements. That's the classical idea. But for these mixed systems, we follow the methodology of this paper, where we enforce weakly continuity on the total flux. So this method is no longer similar to static condensation in classical sense, because the total flux is not directly discretized. But with this construction, we then obtain that hybridizable discontinuous Galerkin method, which benefits from multiple properties like great efficiency. So we actually reduce the whole mixed system to just a single equation, and only for the degrees of freedom on the skeleton. Usually we have much higher convergence rate even for anisotropic cases and convection-dominated cases. And also preconditioning is way easier because the resulting system is structurally similar to like low-order matrices. And thanks to all these, we can move away from like direct solvers, which we typically need for some stiff problems, and use just classical iterative solvers, which scale much better to HPC clusters and typically have overall lower computational costs. So this is then content of this branch Darcy HDG dev in MFEM and the associated PR of 350, which I'm working on. So if you want to learn a bit more or try something by yourself, don't hesitate and check out this break. But getting back again to that mixed systems, how this is then implemented in MFEM. One of the fundamental classes here is what Darcy form. This class takes just two finite element spaces for fluxes and potentials, and also just fine convention. And what it does for us, it constructs the transpose operator matrix. It also constructs that block operator, which you may then use like multiplication. Usually also it can do elimination of the potentials if that's possible. So like in those cases where we don't have any convection, just a pure diffusion or diffusion reaction, we may eliminate the discontinuous potentials from the system. And it also does elimination of essential degrees of freedom for fluxes if we use continuous elements there. So in the end, we may use one of the convenient methods, which you probably know, in MFEM, like for linear system, in this case, it's some linears. So this is an example. Basically, example 5 from MFEM, which is Darcy problem, now rewritten with this Darcy form. So the usage is really simple. You just obtain these few linear forms, and then you add on the integrators like you are used to. Optionally, you may also specify at assembly level, as the Darcy form supports also partial assembly. Then you do assemble normally. But Darcy form does not need to be applied only to the classical diffusion. It can be also the Maxwell problem. So instead of divergence, you may use curl. Like you need, you have then discretization with Nedelix and integral of two elements for magnetic field. Explain basically the example 3, although rewritten this one, and then you get these nice profiles for the electric field, and in the new release of GLVIS, where we have also support for integral element, we may next visualize the magnetic field here. But getting to that convection-diffusion, you have that local discontinuous Galerkin method. So in this case, we take both the potentials and also the flux is discontinuous. And we may formulate it in the following way. And what is key here is definition of the traces. So those variable heads. So this is the general definition of which in turn leads to nature leads to stabilization of the method. And also it draws a link to the hybridization processes. I will share the method in a minute. But for now, for that LTG, we always choose the T22 equal to 0, which essentially means that the traces of potentials are independent of the fluxes. So what we can do is that we eliminate the fluxes from the system. This is now also supported, so we now enable flux reduction. That's under development. So for now, I still not developed convection. But in any case, to give you some example, and a very simple example, only diffusion and centered scheme, and we choose the coefficients like this. And what we obtain is very similar to classical diffusion. And okay, so this is again the Darcy problem with LBG. So nearly the same code. What is new here? We have those phase integrators here. The value with integrator thinks normal trace integrator, and for the stabilization term, we have an HTG diffusion integrator. Okay, and with that, we are finally getting to hybridization. But starting slowly, we take just only continuous Thomas elements for now, and introduce the Lagrange multipliers, and also breaking that continuity of these fluxes and enforcing it briefly through this term and on this spectra constraint here. And discretely, we then obtain this matrix, which is not fully populated, you might see, and from this, we have in the first two equations, and then discontinuous elements in principle. We may eliminate these quantities and obtain in the end just a system for the unknowns, for the unknown traces of Lagrange multipliers. And after the solution procedure, we then return back to our continuous fluxes and potentials. So how is it implemented? We have another class for this Darcy hybridization, which is integrated with the Darcy form. So in the end, all you need to do is to call this method enable hybridization, where you specify the constraint space and the constraint integrator for the fluxes, and eventually also the essential degrees of freedom if you each based on continuous elements. For the constraint integrator, you have this normal trace jump integrator, which corresponds with its constraint, and you could see it. And then the linear system gives us directly the hybridized matrix. And after the solution procedure, you recover MFEM solutions, which us again recover fluxes and it's very simple. And in the code, it means basically just this single extra line having weight with what hybridization. And with that, we are getting to hybridize this continuous parking method. It can also work for convection cases. So the equations are similar, and there are some unit terms here and here you might see. And following this paper, we can construct discrete system, and now we have that matrix fully populated, but the procedure is the same. We reduce the system only to the trace unknowns lambdas. But what is key here for this proper definition of the method is again specification of the traces and stabilization level in the end of like G. So the traces are defined in the following way, where we have a simple stabilization term that we are forcing the local potentials towards the trace values. And when we then substitute the traces of Q by the Lagrange multiplier lambda, we obtain the following definitions of linear forms. I don't know which looks maybe complicated, but again, there are some classical choices, so we need to take the same tau on both sides of the face, like for the centered scheme. This, or you may just simply upwind those values here. So if you remember, we used that HDG diffusion integrator, and that's what magic happens. That Darcy hybridization then takes this integrator and uses that as potential constraint. So instead of just the phase matrix, which is classically constructed, it now constructs what I call HDG phase matrix, which combines phase matrix with the constraint and also the flux and trace matrix stabilization. But from the user perspective, you don't need to care much about these internals. And again, you may use like single line hybridization. So that was the diffusion, but for convection, you might want to do the upwinding. So for upwinded diffusion, there is just a different constructor of the DG normal trace integrator. You might use where you specify the velocity field, or it's also another constructor for that HDG diffusion integrator. For convection, it's then HDG convection upwinded integrator, which is derived from the classical DG trace integrator. But now it works also for hybridization. Or you may use like centered convection, because actually for HDG, even centered scheme for convection is fully stable. So here's an example based on the problem from the paper. It gives like steady state advection diffusion problem manufactured solution. And you might see you need to add on these few lines. These integrators, and I'm like, that we are getting to one a little bit more advanced chapter. So like the numbers that also try to avoid the topic of boundary conditions. Now we are getting to them, but starting slowly, it's just like natural boundary conditions, which are the same for all schemes. We just need to add some extra term to most equations. So to flux, we have some extra term here for potential. Same. But yeah, the Darcy form takes care of that for us, calls the Darcy hybridization and adds automatically that's potential boundary constraint integrators for us to connect it. There are some special cases, but I'm not getting to that now. With that essential boundary conditions, I have already mentioned that. Darcy form can handle it, like for the elements. But what is new here are natural flux boundary conditions with an LDG or HDG method. So for that LDG, we add boundary phase integrator, and this is automatically then detected by HDG or by the hybridization process, and in that HDG is converted to boundary constraint in this form. So we have some extra integral term at the boundary, which was introduced in this PR also for what's it called? Hybridization. And okay, with that we have all ingredients, and we are able then to implement all problems from the paper. So things like steady convection problem, or non-steady Convection-Diffusion, or this Kovácsny flow simulation of contamination transfer. I would like to also mention a new addition in the framework, which is nonlinear convection. So in this case, we generalize now convective term. So we have some general nonlinear flux depending on the potential. And the LDG formulation is nearly the same. And for discretization, we may use the newly introduced framework for hyperbolic equations. So we combine that hyperbolic form integrator with some Riemann solver of choice. It could be the Russanov flux, or newly also Godunov flux. It's defined here. And then the HDG formulation is again very similar to what we have before. Following this paper, we stabilize that HDG by means of integral average of the phase fluxes. So we have like this new method for the Riemann solvers, which analytically calculates the fluxes for us. So we may again use this type of Godunov flux, or there are two special Riemann solvers for HDG, HDG1 and HDG2, which are based on the paper, somewhat simplistic, but actually work quite well. And how it works then, the Darcy form returns us directly the Darcy hybridization object, which then acts as operator. And then we have two levels of global for the Lagrange multipliers lambda, where we use some nonlinear solver of choice, could be LBFGS, also LBB, or Newton solver, because Darcy hybridization also supports operator-based gradient. And then internally, there is another local solver, which we may choose, which solves the local problem with known trace of flux and potential and inverse wouldn't be this system locally inside each element to obtain that local fluxes and potentials. So this is then usage. This is also one of the problems from the paper. Steady state Burger's equation combined with linear diffusion. So and so forth. What we got, the positive diffusion, we just had the definition of the flux function, in our case, Burger's flux, and then we choose one of the Riemann solvers. Is and the hyperbolic form integrator, and that's all. Okay, I would like to also mention another advantage of HDG, which is performance with for anisotropic cases. So even in such simple scenarios like here, you might see that HRT method of steam more performance than classical RTDG, but still relatively comparable. But the main difference comes with the anisotropy. So with some antisymmetric anisotropy, when the heat flux swirls, suddenly classical RTDG mixed formulation is no convergence at all. This sure complements the preconditioner, but HRT is nicely complete. That is a little bit higher number of iterations. And we may play a little bit with this. So this is our problem. And by the way, this simulation with HRT, HDG elements took just like 15 seconds on this computer. Okay, so in conclusion, I introduced the framework for mixed systems based on the Darcy form. Then also the method of total flux hybridization for which the methodology and Cockburn, and this combined together gives us the one-line hybridization. And thanks to that, we enjoy all the benefits of HRT or HDG methods. And also, I mentioned that fresh extensions of the nonlinear convection, and still there are many things to do. Nonlinear diffusion, parallelization, or support for systems of equations, reconstruction of superconvergent quantities, and so on and so forth. So with that, I would like to thank you for your attention.